Bom dia a todos, bem-vindos e bem-vindas a mais um seminário do ciclo de seminário de pesquisa do Centro de Informática da UFPE. Hoje nós temos um palestrante de fora do Brasil, o Jacek Kibilda, que vai falar sobre Designing for Reliable and Secure Mobile Networks of the Future. Então, uma breve biografia aqui do Jacek. Jacek is a Research Associate Professor with the Commonwealth Cyber Initiative and Bradley Department of Electrical and Computer Engineering da Virginia Tech, Estados Unidos. Jacek, muito obrigado, again. Mais uma vez, muito obrigado. And thank you for coming.
Bom dia. Você escuta-me? Desculpe, mas essa palestra vai ser na inglês. Good morning, everyone, again. So my talk is, and let me start my timer, by the way, so that I don't talk for too long. So my talk is about designing for reliable and secure mobile networks of the future. So this work, this is the work that I've done together with some of the students and postdoctoral researchers from my group, but also in collaboration with my colleagues from the University of Oulu. But before I actually talk about some of the technical parts of this work, I want to talk a little bit about the institutions that you might not be familiar with, that I'm affiliated with. So the first institution that actually is my main affiliation is what's called the Commonwealth Cyber Initiative. This is essentially a cross-institutional consortium, an initiative that brings together researchers from different universities and colleges, pretty much all of the universities and colleges at the state of Virginia. And Virginia Tech is the lead site for this. So what is the role of that Commonwealth Cyber Initiative? Well, it is supposed to drive research, innovation, and workforce development. The reason that there are 3 of those pillars is because it's a state-funded initiative. So we actually receive support from the state to deliver on those 3 pillars. Now, myself being interested in research, I'm obviously most interested in the research part. And in the research part, we cover 3 areas, essentially. We cover cybersecurity, we cover AI, and networks. And I'm mostly affiliated with the network side, and actually particularly with the wireless networks. But since I've joined CCI, I've tried to expand a little bit some of my research interests to cover also a little bit of at least the security topic and so on, which is of high importance to the state of Virginia. But the reasons for this, like, we can talk about it later offline and so on. But the general consensus is that the state of Virginia wants to invest in some of those areas, and the way to invest is actually to invest also in research. So this graph is actually a graph that often, when the center gets presented, is shown there. As you can see, it doesn't really show any papers or any grant money being brought in. It really actually talks about the broad impact, so which is the number of jobs that our initiatives create, the amount of money that comes into this back to the state because of that investment. So this is the most important part, and this is the reason why CCI got funded, to actually generate those kind of numbers. But I'm also affiliated with the Electrical and Computer Engineering department in Virginia Tech, and actually I thought that it makes sense for me to even give it a little bit of a shout out, because the students and researchers that end up working with me, they end up also being affiliated with the Electrical and Computer Engineering department, and that's essentially a separate institution within the Virginia Tech, kind of more conventional to a university setting. So it's actually Electrical and Computer Engineering department at Virginia Tech is very highly ranked. It's essentially, according to the US News ranking, it's top 4 global university at ECE. So it's actually currently tied with the University of California at Berkeley, which shows kind of the level of researchers and the excellence of research that is being done with the department. Here I mentioned also some of the titles that some of the faculty at the department hold. It's a lot of very well accomplished researchers. The areas that the department covers are essentially three. This is power electronics, space and atmospheric systems, and wireless systems. So I'm working with the wireless side of things, but there are also other groups that look at power electronics topics. So obviously research is not done in isolation. So I just want to kind of highlight a little bit some of my connections and some of my groups. So shout out to the people that I work with who are here in the in the box, the 5 people that I work with. Like one of the great things, and you can see I added flags there just to show to people also where some of the researchers are coming from. One of the things that I particularly enjoy about research and being in academia is that you get to work with people from all over the world, essentially. And I actually have a chance to work with some of the people also from Brazil. So some of my best students are actually coming from Brazil, from different cities. So currently, I'm not working with anyone from Pernambuco, but maybe in the future, let's see. I also have a number of collaborators. So some of the collaborations come from the Commonwealth Cyber Initiative. That's part of the whole mission of CCI, is to bring the researchers together. But also we collaborate internationally as well. So we have researchers in Finland whom we are collaborating with, as well as researchers in Ireland or Northern Ireland. And here are some photos also of like the recent events, and I added some highlights kind of. So we had a little bit of successes also this year, some best paper awards and some extra grants and so on. So quite a few interesting topics happening, and yeah, just wanted to give a shout out to some of the people I work with. So for today's talk, this isn't really an outline. This is more like kind of a set of things that I would hope at least some subset of those will stay with you. So I don't necessarily foresee that we go in depth for some of the topics, but I'll try to cover at least some of the bases that if potentially some of you are interested in actually going deeper in those topics, that at least maybe you have the right terminology, maybe you have the right idea for what to look for. So I would like to start with like talking a little bit about 6G, what 6G might be and what it is. And then I will talk a little bit about, then I have 2 topics that I would like to cover that are based on some of the research that we do with our group. So one is based essentially on reliability. So we want to look at how we can build the networks, in particular 6G networks, to provide reliability. And so then the question number 2 and question number 3 are related to that. And then another topic that we are covering, which is related again to networks, wireless networks. We want to look at one of the new technologies that is foreseen to be used within 6G, which is called reflective intelligent surface. But we want to look at it not from the perspective of what it can do for the network, but actually what kind of adversarial threats come in from using that technology within the networks. So without further ado, let me go to 6G. So before I talk about 6G, because kind of like 5G is there, but isn't there kind of I looked up the numbers also for Brazil on like how the 5G looks like, and it seems that there is a lot of deployments of 5G already in Brazil happening. So it seems that the operators combined provide over 40% of coverage already over the population of Brazil. But turns out actually something that surprised me as well, but I suspected because I've seen this pattern happening all over the world, is that the population isn't ready to have the 5G. So only 5% of users, about 5% of users have devices that are capable of 5G. So 5G is there, but isn't there yet. And I'm already starting to talk about 6G. And the reason why I want to talk about all the other generations is because I want to explain why I'm talking about 6G in the first place. So I deliberately start this figure with 2G simply because this was the first global system. So there were systems before that, but those systems weren't necessarily global. They were limited in the service that they were providing. But 2G was really the first system that actually hit it globally. And one of the reasons why it was so successful, it was because it was the first fully digital system, meaning that you were able to encode your voice, for example, which meant that you were able to put in more users, you were able to control the quality of your calls, you were able to also then add new services such as text messages, you were able to add later on internet and so on. So that helped the that technological leap actually helped to promote the technology and helped to promote the use of that technology. So about 10 years later, about 10 years later, we had commercial rollouts of 3G. So 3G, what 3G did basically, it focused on the thing that it still provided the communication part, but it actually started focusing on something that was emerging as the potentially the interesting, the new kind of service and the new use of devices, which was essentially that providing that higher data speeds. So the logic was there that the higher data speeds we give to the users, the more services they can use, the more innovation and so on. And something like web browsing, maps, and so on started to appear because of that, because we started providing higher data rates and the users were able actually to start using those more innovative services. Now, they weren't great at the 3G level because the rates weren't still great. So hence, when 4G came, the idea there was that let's give the users even more of that. So let's give users more speed, so that they can actually start using even more services. There's more innovation and so on. One other thing that 4G did is it also kind of the realization was there that perhaps separating voice from data is not beneficial to us, and voice actually wastes a lot of potential, a lot of bandwidth that could be used for data, and data is the real thing. So again, we focused on the speed, and by focusing on the speed, we were able to introduce new services. So now web browsing is a no-brainer. People are using maps all the time. But then we have also some new features. So we have video calls. We have also games. So Pokemon, a couple of years ago, Pokemon Go was a big thing, and so on. So we got a lot of innovation out of this. So the logic was that if we add more speed, then we're going to get more and more of the innovation. So when 5G came in, 10 years later, we started adding more speed. We added a couple of other things like better latency and so on, but we wanted to do more speed. But the problem with that was that hasn't really trickled into new applications. Like the fact that we thought that if we add more speed, then out of a sudden, magically, we are going to start having more applications. And that hasn't really happened. So already a couple of years ago, there was a sentiment that, and this is actually from an article that I wrote for a broadsheet newspaper in Ireland in 2017 about the status of 5G. And it was before the first commercial rollouts of 5G even happened in the world, not even in Ireland. And there was already that sentiment that perhaps 5G is missing something, that we kind of focused so much on like delivering higher data rates that perhaps we are not seeing what actually those technologies are doing and what we can possibly do with those technologies. So what 6G will try to do is kind of trying to kind of reflect a little bit on what are we using those systems for and what actually we want those systems to be. So this is actually those 6 goals here, audacious goals actually. They are taken actually from a roadmap report from what's called the NextG Alliance. So NextG Alliance is essentially an industry-led initiative that was founded in the US to basically build a vision and roadmap for 6G research and development. So when I showed you the previous figure with all the generations and so on, I tried to I gave you the dates partially also to show you that basically every technology happens every about 10 years. So we are currently at the phase where we are thinking of what 6G might be and what is the technological features that it needs to contain, what are the requirements. And the reason why we need that period is we need to have industry alignment. So all the companies that are involved in the ecosystem need to be on board of what that thing needs to be. But then also they need to be aligned with academia, with the government, and so that therefore also funding that's available. But also we need to start building up the hype for the consumers later to be able to buy into the new technology and start using it and start thinking about what that technology could be used for. And with 6G, what those goals are really, they are very different from the goals that would have been in the past. So as you can see here, none of those goals here really talks about speed. I mean, if you really want to think about it, the only thing is maybe digital experience that may require additional high data rate traffic, but the rest of the goals are really not related to it. So there's a lot of discussion about sustainability, a lot of discussion about trust, security, resilience, cost efficiency, but also recognizing that there are technologies out there that are changing the society, such as AI, and such as like broad softwareization of everything. Especially in computer networks, you can see that there is a change happening, and a lot of stuff moves away from hardware towards software. So this is kind of what currently 6G is being thought of. Now, in this talk, this is the last slide about 6G essentially. In this talk, I really want to talk about one piece of it. So obviously, all those goals will be covered by multiple companies, multiple researchers worldwide, and so you need to focus on something. In this talk, I will focus on security and reliability, which are very closely connected to the technologies that are being used for wireless. So the first part of the talk is the technical part is really about reliability and how to provide reliability in networks. So why do we want to provide reliability? So in the standards, there's something that's called a service. It doesn't really mean a lot. It's no longer the same thing exactly as it used to be. The voice service, the text messaging service, and so on, they don't necessarily need to function separately within the network, but they help us define requirements. So there were requirements for reliability defined in 5G, and there will be requirements defined for 6G, and they are currently being defined. The point here is that for us as engineers, reliability is often connected with what's called latency, which is the time it takes for your data to arrive from your source to the destination. And what we want to be able to do is we want to be able to control that time. So we want to be able to control what we call reliability. Now, what are the applications for this? So there are plenty of applications. So obviously, ones that you may have encountered are like VR applications and so on. Now, we are expecting that VR will need to be covered by 6G signals, so cellular signals. So not only your home Wi-Fi, but potentially actually 6G. And we'll need to make sure that you are given appropriate latency. So obviously, from the perspective of a user using VR, if you see a lag, then that decreases the quality of your experience, right? So that's very uncomfortable. But there are some applications where actually high latency may be a huge problem. And those applications are, for example, autonomous driving, potentially industry automation. In those applications, if your data arrives after a particular deadline, your car might actually have already crashed, or it might have already done something else that will lead to a crash. Similarly, in this industry automation, that machine might have done something that has disrupted the industrial process and might have led to an accident and so on. So we want to make sure that for those applications that we don't really cross that deadline, or we cross it in a way that's controllable and that we can manage it. So classically, the way to deal with the problem of reliability, where some information can get lost on the way to the source, is basically to ensure that we have redundancy. So meaning that we create an additional connection that we hope would be independent from that connection, and therefore, at least if we send the same packets through different connections, that one of the packets arrives, and that would increase our reliability. And we can do that, like we can essentially, as long as we have a lot of resources, then we can do that for everything. So today, when I came for this talk, I had basically two other means of backup. So I had my presentation on my laptop, I had a USB stick, and I had Google Drive uploaded to cloud, right? So that increases. So since the laptop, we couldn't connect the laptop, we were able to use the USB stick to upload the presentation and so on to the machine. So obviously, I used redundancy here, so to increase the chances that I will actually be able to present. Now, the problem with this, particularly for networks, is that redundancy is costly. So we can't just like infinitely be throwing resources just so that a particular user will be able to have that reliable connection, especially if it's autonomous driving, we will have multiple cars, or if it's an industry setting, we'll have multiple robots potentially needing that connection. So we can't be throwing all of our resources into a single device that needs that reliability. So we need to figure out how much resources we actually need to ensure that reliability. So this work is really about that. So I will start going now into a little bit more technical details. So the first thing is that I want to make sure that you get the mathematical definitions, and I'll try to explain them, but I'll not to go in into details of all of them. So you're welcome to ask questions afterwards or send me an email. So the idea for reliability is really comes from the definition that is probabilistic. The probabilistic definition, so the first equation that you see there, really talks about, it's a very straightforward way to read it, which is it's the probability that transmitting some number of bits using a particular ring that has a speed that is potentially random has to be done within a certain deadline. So that's tau. And we want to make sure, because we assume that the speed is probabilistic, so it's not a fixed speed length, especially for wireless communication. This is important. And we want to assume that this is over a specific threshold, alpha. Now, the threshold alpha is essentially what we call reliability. And we typically assume that reliability to be in percentage. So the kind of reliability, just to give you an idea, the kind of reliabilities that we care about, and this is at the bottom here, is what we call 5 nines. So we want to have 99.999% reliability. So out of every 100,000 packets that we are sending, we want to lose potentially, we want only one to be below that threshold. So that's a pretty stringent threshold. Now, what we want to do is we want to figure out the amount of resources that we need in our network to ensure that that we meet that alpha. And the way that we try to figure this out is we want to initially look at the amount of bandwidth. What is bandwidth? Well, hopefully you know that, because I'm not going to explain this very well. But the idea there is that the faster you want to transmit, the more bandwidth you need in your system. And essentially, bandwidth is because of that, bandwidth is a very precious resource. Because if you have multiple users, you also have to divide it between those users. So what we do is, in order to extract that bandwidth from that expression, we try to invert that expression and get what we call here the quantile. So in order for us to do this, we need to estimate that quantile. And there are essentially two ways in which we can figure out that quantile. In general, this is a difficult problem. So that's why there is a lot of research on that, but not a lot of good answers. So one of the possible answers is through simulation. So we started off with simulations. And by the way, estimating it at very high alphas requires a lot of simulation cycles. So I'm not going to show this in this talk, but we also have done research as to how many cycles we potentially need to actually have good enough estimates of that quantile. So we did some simulations, and what we observed is that, I'm not going to go into details of those, sorry, but what we observed is two things: that if we want to ensure reliability in our network, the amount of bandwidth that we need may be actually exceeding what we have currently in the network. So what we have in the network, so possibly I hope that it will be seen in the video, but LTE would probably be about here. So everything that's below would mean that we can actually support that. And 5G is probably about here. So anything below could be supported. The thing is that this actually shows a result. This is a result for a single user, essentially. So if we have multiple users, then we can no longer support these levels of reliability. So then we ask the question of, okay, so how can we actually make sure that we can actually support that reliability, provide that reliability? And so we started looking at the idea of redundancy and using multiple connections and how we can leverage the networks that exist out there to help us decrease the amount of bandwidth necessary. So what we observed is actually, if we look at the networks of multiple operators, so we actually look at the deployments that are out there. So rather than thinking about, okay, how many more towers we need to add to ensure that reliability, we started looking at, okay, let's assume that our operators can actually do multiple connections. And if we allow for this, we actually can show that requirement can be decreased essentially by 2 orders of magnitude, which is a lot, which means that now instead of having a single user potentially being supported at that reliability, we can support potentially 100 users at the same time. So that was interesting news, but that was all done through numerical simulations, numerical studies. So once we've observed those numbers and started looking at some of the trends, we started asking questions about the design, technological design. And in particular, we were thinking about, okay, so we considered, you know, how many users we can potentially support with those technologies. But now, if we were to design for reliability, similarly as we design for coverage, so the networks currently, the operators are putting out towers to ensure that you have reception on your devices. But they measure reception by simply looking at those like coverage bars, let's say, to simplify things, right? So how can we do the same thing, but now thinking about reliability? So how can we deploy those networks? So what we thought of is, we thought of these kind of coverage maps. So here on this, on those diagrams, the blue dots actually represent tower locations. The white spots represent the coverage areas of reliability services, and the red areas represent essentially the outage areas. So what we wanted to look is, we wanted to capture how you can actually design those, like how many towers do I need to actually make sure that I have the appropriate coverage and so on, or how much bandwidth. So for example, here we show like that by increasing the bandwidth, we can actually improve our reliability coverage. So in order to do so, and this study we actually decided to do analytically, because simulations would have been actually quite difficult for this, and we can do that through simulation. That plot actually was generated through simulations, but it actually is quite computationally heavy to do this. So we thought that we need to use more analytical tools for this. And I'm not going to maybe explain some of it, but I'm just going to flag a couple of things here. So that first definition, this is essentially the same definition that I've showed you before. I just substituted those first symbols within the probability, but I added one more thing there. I added the condition and this phi, and which represents a point pattern. So in order for us to be able to do this, we used what's called point process theory. Essentially, point processes are random sets of random points. What it means is that we use it for representing tower locations. And the reason we are using it to represent the tower locations, because what we want to do is, if our point process has the right properties, meaning that it's ergodic, if we take a user, if we take static number of static points, and if we take a user, then we move that user around those points and around this area, which would essentially boil down to coloring all of those patterns, then we should get actually the numbers that represent those patterns. So we should get that fraction. What is the coverage? What is my coverage? And so if we use that logic, then that number should be this eta here. That should be our number. The problem with the the problem with this is that it actually, in order to do so, we need to introduce an additional probability. So the probability that we had here becomes embedded into another probability. And that's something that's called a meta distribution. And in general, it's not very easy to work with. And if we want to extract the bandwidth, and you can extract the bandwidth from this, you get this like very nasty expression. So it's essentially the inverse of a cumulative distribution function of an inverse of a cumulative distribution function, and so on. It sounds horrible to work with, but actually, as a matter of fact, it's fairly easy. Well, easy is the wrong word here, but it's actually possible to figure out an expression that will represent that inverse of an inverse of an inverse, inverse of an inverse of the CDF. So what we've managed to accomplish, we've managed to accomplish those expressions. And I'll say why those expressions matter now. Those expressions matter because as we start simplifying them, we start observing the law that governs the amount of resources needed and the reliability. So here in this case, this alpha pops up here. What it means is that our bandwidth is inversely proportional to alpha. But what it means is that if we add 9, so if we move from like 9.9.9, so we add one more 9, we actually need one order of magnitude increase in bandwidth. So we need 10 times more bandwidth. So if I want another 9, instead of 10 megahertz, I need to have 100 megahertz, and so on and so forth. So that's a very neat way, and very nice expression. And if we compare those expressions against our simulations, we actually see that this law holds very well. Why would we need that? Well, we would need that because we then can very easily estimate what is the coverage that we get for our systems. And we did that same study also for the multi-connectivity with multi-operators. Now, the expressions here are not that nice, so this law is kind of not as neat, but we kind of can roughly estimate it to be that every 2 nines now require an order of magnitude bandwidth. Again, so we were able to establish a very nice relationship between those parameters, allowing us to plan for the network potentially and be able to dimension that network. And here is a comparison of those for multiple operators. I can skip that maybe. I can maybe skip the key takeaways. So, do you have any questions? But I'm happy to answer the questions afterwards. Just maybe for this, in the sake of continuing and finishing in time. Another topic that we looked at is the security, and we looked at the security of one particular technology that will be part of 6G, which is called the reflective intelligent surface. So the idea here is that what is reflective intelligent surface? Here you have 2 examples of, one is actually reflective surface, the other one is refractive reflective surface, and I'll explain the difference in a second. So the idea behind the reflective surface, it's essentially a surface that's composed of many small reflective elements. And those elements are reflective because if you illuminate them with an electromagnetic wave, they'll be able to reflect that electromagnetic wave, and with certain laws. But the cool thing is that you can control that reflection. So it no longer follows the Snell's laws, but you can actually change that, right? So by changing the electrical properties of those elements. And what it allows you to do, it actually allows you to achieve, first of all, better coverage. So you can actually control where you want to send your signal after it has already been transmitted. And you can use it for also other applications that I mentioned here, sensing and positioning. And the 2 examples that you see here, one example is actually a prototype surface from Arizona State University developed by my colleague. We are working on a joint project together. So that surface actually has 800 of those tiny elements. It's actually very small, kind of like this size. But it is able actually to reflect communication signals. And another example here is this is a prototype from a company. So this is actually, I called it refractive reflective surface because it can be embedded in a window. So it can do 2 things. So reflect the signals, so actually bounce them back in some direction that you can control, or refract, meaning that it can pass through the signals, but it can pass through them with an angle that you decide. And that will depend on how you electronically control the elements within that surface. So why are we interested in that technology for 6G? Well, the reason is that the coverage that we expect for we have already expected for 5G, but even for 6G requires a lot of deployments, and deployments are very expensive to put out base stations, put out towers, and so on. They are very expensive to deploy. They are very expensive to maintain. So surfaces are potentially a cheap way to improve that coverage without necessarily investing in all of the additional infrastructure, meaning power supplies, meaning shelters, and so on, or encasings. So they are potentially low power. Depending on the design, they may be very cost efficient to build, and they are very easy to extend. So I mentioned that one surface can be of this size, but you can actually, if you design them properly, you can actually stack them or extend them. So you can actually build like huge surfaces. And they are potentially also easy to install, depending on like the kind of applications you have in mind, and so on. So they have a lot of cool applications. So why do they work? I try to give you at least a tiny bit of an idea for why they work and how they work. So that at least you don't, so that you have at least an idea of when I actually show you the actual work that we've done, so that you can kind of get from where maybe our ideas are coming from and where you can improve things. So the idea, if you have wireless transmission, the idea is that you want to transmit your signal, X, to your receiver, and at the receiver, that signal becomes Y. First of all, because you get noise that's added to the receiver, to that signal, so that noise will corrupt the signal. But also what corrupts the signal is the channel. So the fact that the signal has to propagate through that wireless channel, and that corrupts the signal. So that's the very classical definition of a wireless system. Now, with a reflective surface, what happens is that the emission isn't going in just one direction, but actually, in fact, it goes into multiple directions. So some of that, if you have a surface, some of that transmission will also go in the direction of that surface. What the surface does, it actually, if you control it properly, it is able to bounce that signal into the direction of the receiver. So what happens now is that that signal also has to pass through the wireless channel. So it has to pass it first before it reaches the surface and after it reaches the surface. So what happens is actually at the receiver, you get your first channel, but then you get also the signal coming from a different path through the other channel. And the cool thing about this, and this is where the reflective surface and the intelligence come in, is that surface, there is a parameter that we can control. So we can actually change this whole expression here. And we can change it pretty much arbitrarily. So here I wrote plus, but as a matter of fact, if you set it up properly, this can be turned into minus as well. So this is like the very basic idea for how a reflective surface would work. Now, where the malicious part comes in, I talked about the coverage expansion and so on. So if this is weak, then you can see that the user will still get this. So this is where your coverage expansion comes in and so on. But now, if you actually change it properly, then you get a minus. And this is where things start to become interesting. So you can actually assume if you assume that potentially that surface is used by an adversary, you can assume that the adversary uses the fact that the surface is easy to install to deploy its own surface and potentially destroy your coverage, cause an outage. But because it's cheap to design, you can also assume that it will probably come with a microcontroller that's easy to hack or easy to break into. So there can be a legitimate surface, but someone may actually hack that surface. Or if that surface is actually intelligent and it's using some machine learning algorithm, you may potentially assume that that machine learning algorithm is designed based on some training data that might have been faulty or might have been corrupted by someone. Or potentially even if it contains appropriate backdoor, it may be the input may actually trigger some malicious behavior of that or some faulty behavior of that surface. So there are various different attack vectors. Now, in this work, I'm not looking at the attack vectors. We are looking at the attack themselves. So actually, a malicious service, what it can potentially do. So one of the first attack and the most basic ones is what's called the cancellation attack. So this is when I mentioned that here we have that basically the same system as before, and slightly more complicated version of that equation, but just simply contains more parameters. But the idea is the same. So you have your part that comes in from the direct signal, and then you have the second part that comes through the reflective surface. And we have our parameter here from the reflective surface. Now, the goal of an attacker here would be to set those parameters such that this whole expression results in a minus here. So that whole expression is, if that is a minus, then it means that the signal that will be received at the user will be smaller than it would have been before that surface was actually used. So the question here becomes is how we can actually set those parameters such that that signal is actually smaller. And to do so, we can set up an optimization problem. And basically, the objective function of this is actually to minimize the amount of power that user receives. And our variables are essentially the parameters of that surface. Now, that problem is actually difficult to solve, especially if we are talking about the realistic sizes of those reflective surfaces. So even for like hundreds of elements or thousands of elements, this is essentially impossible to solve directly. So what we use heuristics to solve that problem. So you can actually come up with quite efficient algorithms that will solve it, but they won't arrive at global solution, or won't necessarily arrive at the global solution. But turns out that even with those heuristics, we can actually show that the attack can be very powerful. So a system without the attack, so you can see in the different colors, a system operating without the attack, and all the markers here, a system under the attack. You can see that for a system where we have, this is based on antenna sizes and the location of the RIS. So actually the location here, one thing to note is that the location of the RIS with respect to the transmitter and receiver is here. It actually matters a lot. But what you can see is the RIS is conveniently positioned. It is actually able to reduce the signal from 20 dB, or about 20 dB, to minus 40. Essentially, 0 would be a point where there's no reception, like you're not receiving anything. So actually the attack can be very powerful, but the problem with this attack is that it requires a lot of information. So for us to be able to, what it really means. So first of all, what does this plot mean? This plot means that we need to have exact information about our scenario. So the less information we have about our scenario, the less powerful the attack becomes. So and it becomes less powerful very quickly. So what is the information that we need? The information that we need is essentially all those HC, HD, HA essentially describe to us the scenario. So they describe the wireless propagation. So they describe the locations of the transmitter and receiver, the locations of the surface, but they also describe the entire wireless environment. So all the reflectors, other reflectors, or the scattering, all the diffractions that happen. And in order for us to acquire this information, this is very difficult. It's a very difficult problem. So we are unlikely to have perfect information here. So we are more likely to have imperfect information, which means that the attack probably will not cause any damage, which is a good thing from the perspective of security. So here's the thing. So that's what we were thinking then, is that, well, so this was not a very targeted attack. This was just a dumb attack, kind of not a jamming attack, but an attack that was kind of not taking into consideration the actual wireless protocols. So what we started to look at is we started to look, okay, so what would happen if we are actually assume that we know something about the system? So one of the technologies that we thought we would try to attack is what's called massive MIMO, and in particular, multi-user massive MIMO. What is massive MIMO? Very briefly. Again, there's a lot of different topics that I can spend an entire lecture about. And I'm trying to cover them in essentially what amounts to a paragraph. But the idea behind massive MIMO is that transmitter that is equipped with many antennas. In this case, we call it massive because the number of antennas would go into hundreds. Can actually create a signal that will be sent to a user with a much higher signal strength. Now, for multi-user massive MIMO, what we actually assume is that because we have so many antennas in that transmitter, we can actually create such a signal that can cover all of those users simultaneously, both simultaneously in time, but also simultaneously in frequency. So those users are what we call separated in space, because the way we design our signal here allows for those users to receive it essentially kind of separately. The way we achieve that is in order for us to achieve that, we essentially need to do the same thing that a reflective surface I've mentioned before is doing, which is figure out that channel that I mentioned. So figure out that entire wireless environment. And the way we actually do this, and that's where the protocol is. That's how the protocol is designed. We sacrifice some of our transmission time to what we call a training phase, which is essentially the users and the base station, they transmit known symbols known to each other. They are described in the standards. And from those symbols, they try to figure out what's the environment. Once they figured out what's the environment, they start data transmission. So they design those transmission patterns and they start transmitting data. So here's our thing. So this is the protocol, right? So the question that we've asked ourselves, okay, so what if a surface is active during one part of the protocol and not the other? Would that cause a damage? That seems like something that could easily be done, and you can easily synchronize with this protocol and switch the base station on and off. So so before I say this, so this is the same equation as before. This time I added index k here just to represent a single user, because with multi-user massive MIMO, we can potentially target multiple users at the same time. And it's slightly more complicated because there are a lot of signals being transmitted at the same time. So again, slightly more evolving, but it's the same idea that we have that surface, theta parameter of the surface within our system. So for our surface to actually disrupt the system, what we want to solve is we want to solve a slightly different problem. This time we no longer care about this part because we are disrupting the protocol. We just want to produce as much disruptive signal as possible. So we no longer want to cancel anything. We just want to produce a disruptive signal. So for us to do this, we want to maximize this expression, which essentially maximizes the amount of that disruptive signal that the surface is producing. The problem with this is that it's still not easily solvable. All those problems, essentially, like permutations of that problem, will still not be easily solvable. So here we are using another type of a heuristic to solve that problem. Turns out again that with that heuristic, we can solve that problem and actually, again, have a very powerful attack. So those gaps here, they essentially describe the loss of data rate that you incur when you actually apply this attack against that protocol. So if actually during the training period you are inactive, where during the data phase you are actually being disruptive. So by doing that, we actually now not only we kind of we saved ourselves potentially on acquiring the information that is needed. So we no longer have to acquire the same amount of information as we had before, but we actually potentially don't need to also be active all the time. Oh, that's my timer that tells me to stop. I'm actually very close to stopping. So there is a lot more attacks to be explored, similar to this one, that exploit the protocols that can be very powerful. These attacks are potentially much more difficult to essentially to prevent, because they exploit essential features of the protocol, and they potentially can affect multiple users. So there's a lot of work. We have shown that to actually prevent this attack, you need to design a new receiver that is able to discriminate against that attack. I'm not going to show this because it's a little bit too technical, but I just wanted to show that potential. And there is a lot of works. I have it in backup slides, but there is a lot of works actually trying to exploit various different protocols, including geolocation protocols, including protocols that are used for random key generation through wireless and so on, that can be shown to be very disruptive. So that essentially concludes my time. I'm gonna skip this. So here are some references. The papers on reliability are there. There's quite a few of them already. On security, we have two, but there are a couple of others coming in. We are starting to explore all the various attacks, and so you can check on Google Scholar and ORCID any new ideas. And yeah, that's pretty much that. Thank you.
Jacek, thank you for the inspiring talk. So we have some time for questions, either from the audience on YouTube. Se vocês estiverem assistindo aí no YouTube e quiserem fazer perguntas aqui, a gente pode ler, traduzir na hora. Or the audience here. Why they are thinking? I have some questions.
Sure.
You brought a very interesting topic, that is physical layer security. Because people often forget that behind bits and bytes of the digital world, there's an analog world, where there are signals and systems that are connecting, and you brought some light about the difficulty in solving some attacks, and you mentioned the word heuristics sometimes. So I'd like to hear more about this. How mature are these things in terms of detection systems, basically? Because we are talking about. I would be interested in detection systems for this type of attack that is below the digital world. So do you have some ideas about how mature are these heuristics you mentioned in your talk?
So when you say heuristics, you mean just the algorithms themselves, or you're talking about actually the detectors or detecting the attacks?
But maybe the combination of both. So
Okay.
if they exist, I don't know if they exist or already or not.
So those the heuristics, they're kind of essentially a couple of different approaches that people have been using to solving similar problems in wireless comms. So a lot of the heuristics that I used and the community uses for solving the problems with reflective surfaces have actually been ported from heuristics used for problems such as massive MIMO, where you have to figure out how to set those essentially those emissions when you have multiple antennas on the transmitter. Now, with the reflective surfaces, the problem becomes more difficult because it's not clear that you will have all the same information that a transmitter will have. So that actually complicates a little bit the problem, which means that essentially when I'm using some of those heuristics, I'm kind of assuming that I have the perfect information. So what I would say is that one of the big challenges, at least for reflective surfaces, is, and there's a lot of actually works that do not use heuristics, but actually use AI. And so there is a lot of people have been using different AI approaches to either make the decision or actually try to estimate some of the information that we need and then make that decision. So this is still a very much unsolved problem, what exactly to do and how to have robust decisions as well in the presence of this uncertainty about the information, in the presence of uncertainty about the data that you have. So I think there is still room for improvement. There is a lot of works. So I think the challenge here would be to figure out a new approach that actually will stand out because it seems like people have tried everything, but I know that this hasn't been very successful. So I think especially that robustness, I think would be an interesting question. And forgetting about the attack for a moment, because essentially attacker solves a very similar problem, if not the same problem that that we need to solve for non-adversarial applications. So that question of robustness, I think, exists out there. In terms of the detectors, I guess this work on security, physical layer security, actually bridges some of the old ideas, such as jamming, kind of that has existed out there, and in particular in the US, this has been like a big topic in the defense sector and military sector. And so there is a lot of detectors on detecting like very simple forms of jamming, where you just like blast a signal, and that there's quite a lot that you can do to mitigate that. But when it comes to questions such as this, where someone actually tries to break the protocol at a level below, because typically we think about breaking the protocols at, like, as you said, that we're already looking at the packets and so on. Below that level, then things become very complicated very quickly, because typically our receivers are not designed for this, right? So you need to seriously extend those receivers. And it's not clear also how, so first of all, there is very few works that actually explore that. And it's not clear how to do it in a way that's, again, robust, like how you know, can we prevent all the types of attacks, or just this particular one that we've shown here, right? So I think there is a lot of questions. A lot of them would actually be on the physical layer, probably. So you need to kind of go down to address them, and possibly some of them will connect also with questions related to how good your algorithms are, how good is the information that you have about your system, and so on.
Okay, thank you. There's a comment here, excellent presentation from the YouTube audience. A question from George.
Thank you for the presentation. As a machine learning guy, I have one curiosity about the data, because in some slides you show that there are some simulated data. How easy is for you to get real data, and is it very different from the simulated one, so you can take some conclusions from the simulated one and apply to real data? How do you deal with in this?
Yeah, these are actually a couple of questions. So let me try to address in an order that I think is the right way to address them. So one question is, where do we take the data from in wireless? So there are very few data sources for like pure wireless data. very few reliable data sources, I must say. There are a couple of research groups that have actually tried to collect some data and create repositories that you can use to actually then test your algorithms and test your ideas. But these are very limited, first of all, and potentially potentially not very robust, meaning that you may not have like huge amount of samples. So actually, I attended what is it, beginning of November. There is this industry forum called the 6G Symposium, where essentially most of the same companies that are part of the Next G Alliance, they come in and they talk about like, oh, okay, like what do we want to do with 6G and so on. And one of the big topics that was there was actually how do we create data sets that are certified, that companies themselves, how can they produce data sets that researchers, for example, can then use to test benchmark their algorithms, test their algorithms, develop new ideas. Because the reason why those talks are happening is because so far, I think the wireless industry has been very conservative about sharing any sort of data, assuming that essentially it's not part of it is possibly security issues, but the other part is really being sensitive to competition, I think. Just not showing exactly what your system is doing, because maybe if we reveal too much data, then our competitors will know what are the weak points of our equipment, right? Or what are the weak points of our networks. But I think that mindset is changing a little bit now, and hopefully we are going to see in the future some real initiatives where the companies actually produce real high quality data because they have the time and they have the potentially the resources to produce it. But in general, this is a big problem. So that's one answer. The other answer is that there is a big difference between simulated and experimental data. And if your simulations are very coarse, it's not really clear that the solution that you're proposing, the solution that you build based on simulated data will actually work when you actually move it to an experiment. And I'll give you an example. So a student of mine who has built reinforcement learning based system for optimizing essentially kind of a system similar to massive MIMO. He was trying to make sure that the emissions that your transmitter is producing will actually be as secure as possible, meaning that it will emit as least signal as possible towards unwanted locations. Again, difficult problem to solve, so he applied essentially reinforcement learning approach, and in simulations everything works perfectly. He tested on various channel configurations, so on, very robust solution, and so on. He ported that into experimental setting, of course it's not exactly the same, but same size antennas, very similar setup, very similar distances, and so on. That system was basically able to work only within the lab if you don't move anything, if you don't change anything. The moment you changed everything collapsed. Yes, and he brought and he thought he kind of solved this problem, but he brought it to a conference for a demo presentation, and the system just didn't want to work as it should. And I think the problem is really that there is a big difference in the data that you can control in the simulated setting and the actual real world. Now, this is a very long answer already, but the last point is there are some attempts now at building those like very high fidelity simulators. They are often called digital twins, where you essentially produce. There is a way to produce wireless data that with high fidelity, which is called ray tracing. Essentially, it's very computationally heavy, so people don't do it unless you have a very particular scenario. You can do it for a particular loom, for a particular location, and then you can kind of like see how, for example, the access point that you have for a base station, what it will do. But there are some attempts, and in particular, this company NVIDIA, they are looking at developing these kind of simulators that can produce this kind of data efficiently. And I haven't worked with this data, so I can't testify. I think they have had some progress, but how big of a difference between the data produced by these high fidelity simulators and the real world is, I can't tell you. I haven't worked with it. I would guess that there is still some gap, but yeah. So that's a very long answer to your question, but I thought this, like, you gave me at least 3 questions there.
Thank you.
Hello, Professor Kibilda. Thanks for the talk. Actually, I have a couple of questions. I don't know if you have available time for them, but if not, I can reach you out through the email. But the first one is something that you mentioned in the beginning of our talk. You said the Commonwealth Cyber Initiative is state-funded, if I didn't get this wrong. And is that a special interest from the state of Virginia in this kind of topic? And I assume it's something related to the military history of the state, but if not, I'd like you to discuss a little bit more about this. And the second question is a more technical question. You've mentioned about the 5 nines factor of reliability. And my main questions about this is this number, is this factor related to some specific application area, for example, autonomous driving or something like that? Or can you transpose this to a different type of application?
Okay, sure. I'll answer the technical one first, if that's
Okay.
So yes, that number 5 nines, it's actually kind of related to, it is and it isn't. So this number oftentimes is application specific. So so for example, currently within the NextG Alliance, one of the things that we've been looking at is trying to essentially make the same calculation that I presented here, but for a different set of applications. And when we, and I say we, I mean, it's really not me, it's really some of my colleagues who actually work for companies that actually develop some of those technologies. They figure out what is really the reliability that that particular technology needs to then be connected with some quality of experience. So generally speaking, it seems that this is very much dependent on the technology. So a lot of the technologies would require either 5 or 6 or 7 nines, even at certain cases. But that number, so my honest opinion about that number is that it's really more an educated guess than an actual need of a technology. So it's done based on some technological features and some observations, but observations of the quality of experience. And quality of experience is something, of course, there are measures of quality of experience, but it's always very subjective what that quality of experience is. For certain types of applications, such as, like I mentioned, autonomous driving, and so on, I think we really don't know, right? Because I don't think you can even make a computation kind of that says, oh, with, you know, if you have 5 nines, then you will your electric or autonomous vehicle will definitely kill a person, and if you have 6 nines, then it will never kill a person. I don't think anyone can ever say that. So I think it will always be a little bit subjective what that number is. The 5 nines actually come from 5G. I have not been a part of the discussions about 5G, so I don't know exactly who selected the number. I know like how those numbers are being selected for 6G, and yeah, but in my opinion, it's more of a subjective process than an actual kind of like very scientific kind of. There's no law that says, I think, that it has to be 6 and not 5 nines. And to answer your first question, I guess, yes. So this is a state-funded initiative. The reason for this is because, I mean, in general, not only in Virginia but in the U.S., there is a workforce gap essentially, and that workforce gap I think can be extended to STEM, so all science, technology, engineering, and maths. But in particular, there is a very large gap in the US in cybersecurity research. So the AI part and the networks part, they kind of are added because I think at this point they are a big part of it. But it's really about the cybersecurity, at least for the state of Virginia. And our main mission, and this is what I mentioned earlier, is that those numbers, they don't represent the numbers of papers that we produce or anything that we could. They really look into those the workforce and the economic impact. And the reason why Virginia is particularly interested in cybersecurity is that, and I think you've touched a little bit on this, is that Virginia is actually, first of all, there is a lot of defense presence in Virginia. So there is there's the Pentagon. I live, next door to Pentagon essentially, but there is also other agencies that are located in Virginia. But what that means is also that because there are those agencies, there's a lot of companies also out there in Virginia that are located because of that proximity to the federal government and so on. And a lot of those companies actually then end up working either in national security or cybersecurity and so on. And that's why, particularly in Virginia, there's that gap and there's that need to develop that workforce. So something that I don't mention here, I mean, the research that I show here, like it's really done by PhD students, right? So you need to have certain level of qualifications to be able, and certain level of background to be able to do some of that research. But what the state really cares about is us even going out to essentially to undergraduate students and going out even to what's called community colleges in the US, so 2-year colleges, and trying to figure out how to kind of get these people interested in cybersecurity, how to get them, how to give them some skills so that they can enter the workforce and so on. Perhaps not necessarily solving these sort of problems, this is for research, but actually maybe kind of using some of the research that we do to then maybe attract some of these people into the field, maybe kind of give them a little bit of the technical background so that they can enter various jobs. So there's a very big piece of CCI that I don't show. I'm also not the executive director of CCI, so so he does those talks and so on. He has a lot of slides about the workforce development programs and innovation programs and so on that the whole CCI does. But it's a large organization, essentially around 300 researchers.
Okay, thank you very much.
Sure.
Questions, I'll reach you out through email.
Sure.
Any other question? Yeah, I forgot to mention that CCI is a partner of the Centro de Pesquisa Aplicada. We've just approved here in cybersecurity. So, yeah. What advice would you give to students who might be interested in reaching you, Jacek? Because there are some students that may watch your presentation later on YouTube. So you said that you already have some Brazilian students and maybe some from Pernambuco or even researchers that are no longer students. How can they reach you? Actually, it says drop an email, make a call, and what kind of advice would you give them?
So the way to reach me is very straightforward. Just use my email. Like if you don't see it in the presentation, you can find it online. I'm actually very analog, so email works best for me. It's almost like an instant messenger with me. So feel free to reach out. I mean, in terms of the general advice, I think kind of it really depends on what you want. So I think maybe I'll start with researchers. If you're a researcher and you would like to collaborate with the US the same way as we collaborate, I think sometimes it's as easy as just send an email and say what is your plan, what is your goal, right? Of course, the easy way for us to collaborate is if someone has their own funding and comes in, and then we typically, if the topics match and we think that it makes sense for both parties, then we host the researchers, and we've done this in the past also. There are some topics that, for example, that I know that are very big in Brazil that I have not covered in my presentation, but I actually have. I'm starting to have students that look into those topics, which is called Open Run. So actually building those softwareized and disaggregated mobile networks. And we are looking also at some security aspects and so on of this. So there are some topics that we have active collaborations with Brazil, and we had researchers from Brazil coming in to basically exchange ideas and so on. So I would say it's really kind of about reaching out, and then from there on, we try to figure out what's the right mechanism to host that researcher. Because if you're not self-funded, we need to figure out what is the mechanism that we can use to host you, and we can start that collaboration. And what I would say in general, for me, what has worked in the past is the more concrete you are kind of in your ask, the easier it will be for us to figure out how we can collaborate and so on. So yeah, that would be my advice to like general researchers.
Mm-hmm.
For prospective students, I guess for students a little bit different. So there is I mean, first of all, you need to be interested in the topics, right? So I would say to the student that, check out the topics, see what's interesting you. Don't try to force anything, kind of. So just because, I don't know, you want to go and live somewhere, or like try to live in the US or somewhere, doesn't necessarily mean that you should like go and jump into the first opportunity that happens there. I think you should kind of look a little bit into opportunity, do a little bit of your own research as to what are the topics that some of the researchers cover there, and then try to reach out to those researchers. If you are interested in the topics of a particular professor, particular researcher, one thing that you have to know about, especially about the US, that the process for application to pretty much all of the universities in the US is about the same. Meaning that you would be expected to have an English certificate. You might be expected to have what's called a GRE, which is like the competence test. And you will be expected also to have your documents translated into English and so on. So there are a couple of things that you would have to plan. So if you are thinking of studying in the US, you can't make an instantaneous decision and like, oh, tomorrow I'm making application. No, because it will take probably at least 6 months before you can actually get admitted to the university. So it will take you some time to get the documents, get the certificate, and so on. So if you're thinking about this, then start looking at researchers, start looking at the requirements, start looking at, do I need to get an English certificate? What would that English certificate be? And so on. What's the level of that English certificate and so on. But if you're just interested, and if you think that the topic is right, send an email. You can always ask. I'm happy to kind of to answer questions, especially from people who are interested in the research topics and so on. And I can then, of course, provide some guidance and so on as to what to do. But oftentimes it takes quite a long time. And currently, for example, I have students that I'm in conversation with about joining in the fall of 2024. So when I say fall 2024, I mean August 2024. So, yeah. And we've been in conversation since pretty much September, October. Because they need to get the English certificates and so on. That's pretty much for most of the American universities, that's how it will work. So the good news is that if you have all your documents, then you can possibly apply to multiple universities. But the systems differ, and it's also different in Europe, right? So if you're thinking of Europe, the system is slightly different. And I think the best way to actually figure this out is to reach out to some researchers in a country that you're interested in, and try to see from there, but do your own research as well.
So thank you. There's another comment from a colleague of us. Thank you for such a nice presentation. Very interesting topic.
Thank you.
Any other question? No. Last question from my side. You mentioned in the beginning of your presentation about the age, the hyper low latency communication networks, and that will meet 6G. Yeah,
6G. Yes.
Have you been touching time-sensitive networking or it's something that you because TSN is a set of standards used individually or combined to achieve a given goal. So it's been investigated for years in the IEEE 802.1 group, and it started in local area networks, and it's now in industrial control systems, in cars, etc. And it's been arriving in wireless communications as well. So how is your perspective about TSN if you have been working or not with this?
I haven't worked with TSN, nor for wireless nor for wired networks. Okay. I know it's coming. I think I don't know what's the status of it, but I think it's still kind of, as you say, it's coming, and it's because I've heard about it's coming to wireless for many years now, and it just doesn't seem to be translating into popular standard. There is definitely a lot of interest in that. So some of the works that we do here and some of those questions of latency are definitely connected to time-sensitive networking, in the sense that what I was looking here at is really kind of from the perspective of just the wireless part. So forgetting about the protocols that you have in the network, like what can we do from the wireless side to actually to cater towards those ultra reliable, low latency scenarios. But as a matter of fact, if you really care about the time sensitive networking, then this is the way you want your network to operate, why wouldn't you change also the protocols in that network, right, to help you with that? So so I think there is a big question, especially when it comes to 5G and 6G, because one of the things that I have not mentioned here is that, and that's becoming kind of big in 5G, but probably will really come in 6G, which is called private networking. So another way of deploying networks, and rather than providing it to a large customer base, is try to figure out how we can build essentially like those islands kind of within our networks, just provide deployments that for, let's say, for a campus, but more likely for a company, for some factory, maybe for a military base or some other place, that will operate using the same principles as the rest of the network, potentially using the same spectrum, using the same type of technology, but actually would provide a particular service with much more controlled service to that location. So that is still big part of research, and I think that's where scenarios such as time-sensitive networking have a bigger role, because if we assume that we want that very low latency scenario, then we probably want to make sure that we not only optimize the wireless side of things, but we actually optimize the protocol stack. And if we think about, I'm adding like a lot of topics now, but to the mix. But if we think about open run and authorization of networks, where you can potentially easily replace parts of the protocol stack, then I think kind of, if everything comes together, then yes, that there will be a lot of space for time-sensitive networking. But I don't know really what's the status in terms of how well it connects with what is possibly envisioned for 6G. At least from what I know, for now, 6G is not really considering any kind of convergence between time-sensitive networking with time-sensitive networking, but we'll see.
Okay. Any other question? If there are no questions, let's start.
Thank you, Jacek. Thank you. Obrigado, Jacek.
Com isso, a gente encerra o seminário de pesquisa.